what happens? What?
Increase
Why?
your area.
Very good. So, like your colleague mentioned, well, your thrust with all of a sudden start burning, and then your thrust will continue to increase, primarily because the area keeps increasing because it's radially burning outwards. That's what we call refraction rates. These are what we call refraction rates. How quickly are we burning within the solid? And it becomes very, very challenging in terms of research specifically. We don't understand how this works in the detailed perspective from the flames and reactions behavior, because it's very hard to measure some of these characteristics that are here, because it's highly luminous, and the issue too is it's solid, it's a material, so it's very difficult to probe because you're primarily burning and you're inducing a gas, so it's a multi-phase type of problem. It's very challenging to understand it, but what we have is bulk assessments of, well, if you put this much quantity of fuel, this is what you get. That's ignition pressure and thrust. That's what we know. Okay. Now, how to flatten out that thrust curve is to go and shape your fuel in a star-like form, something like this. And by doing this, your thrust over time is not only going to be constant. Something like this. To show you examples of both, I have both here. Right here. So this is a liquid rocket engine, and what you're seeing here again, there's your thrust chamber right there. That's your massive CD nozzle, right? And these are your inlet nozzles, which are mixing both your fuel and oxidizer. These are your fuel and oxidizer lines, and as you can see right there, what you're seeing here is the gas generator, which is primarily what we call a gas turbine engine, compressor combustor turbine. You're generating shaft work or exhaust gases to drive a turbine. That turbine is driving a compressor. The compressor pumps in the fuel and the oxidizer here, because the ignition pressure here is very high. So you know that this pump is actually a very, very strong pump. And that's why you will actually see in some of, if I show you some videos, you will see some exhaust that's coming from the side of the rocket. That's this, the gas generator, primarily exhausting on the side. And if you look at the rocket itself, you got fuel, you got oxygen, and this is your payload right here. So you're pretty much carrying all your fuel and oxidizer there, and then it's disposed of at the end. Plus, you're trying to capture it like being done later. Anyway, so this is an example of a solid rocket where you can see your fuel right here, all around the liner. You've got the CD nozzle, and this is your throat right here, and what you're seeing here, obviously there's an igniter. This is the star-like pattern showing you the different thrust behaviors that come around. This is the thrust over time generation. There's a concentric fuel burning characteristic as well you could do. This is another trick, and these are different other tricks to neutralize your thrust behavior. But this just shows you different patternation that you can get thrust in, depending on what your mission is with the rocket. So missiles, and ballistics in general, you might be choosing different type of behaviors. Okay. Now, some of the missiles have gas generators on there, so air-breathing rockets or air-breathing engines on there. So something to keep in mind. Okay, so moving on, let's let's characterize some of the masses that this rocket has to carry, and let's do an example on it. So we got mass right here, we got the mass of fuel, mass of oxidizer, and total propellant mass, so we want to characterize our rocket engines. You've seen this before. So let's take single stage rocket. So I have my payload mass, some definitions of the different masses that we have to deal with. MP, propellant mass. MS, structural mass. MO, initial mass. And MO is equal to the payload mass plus the propellant mass plus the structural mass. MB, which is the burned out mass. Burnout mass, where I expelled all my fuel. Mass of the payload plus the mass of the structure. R, which is mass ratio. You kind of define it, initial versus final, which in this case will be MO divided by MB. And it's equal to MO divided by ML plus MS. Because I'm still going to have my load, and I'm going to have my structure at the end, once I've burned all my propellant. So we'll think of it as the range that we were computing with air-breathing engines. Lambda, which is our payload ratio. These are very important because that's how you characterize your thrust for your rocket engine. So it's the mass of the payload relative to the initial mass minus the mass of the payload. And you can say, well, it's ML divided by the propellant mass plus the mass of my structure. And we want to maximize this because otherwise we're not going to be able to carry a huge payload. So maximize. Structural coefficient. Is essentially the structure mass relative to my payload mass plus my structure mass. So that's equal to the burned out mass minus payload mass divided by the initial mass minus the payload mass. And again, maximize. So from those two, I could say, well, my mass ratio R is equal to 1 plus lambda over eta plus lambda. So if I know all these different masses, I could characterize, characterize my rocket system. So let's do a quick example on this. This is a review, right? This is not something new that you're seeing for the first time. Spent aero students, right? Most of, no? Orbital mechanics, space systems. Some people are nodding their heads and some people are saying no.
Those aren't required classes.
Oh, okay. Yeah, but both of them. You have to take one.
Should be.
Or another. You can take orbital or
They don't
space
make you
systems.
take any space classes, dude.
Okay.
That was
You're
the
seeing
old.
it right now,
We're
right?
thinking of the old catalog. The new catalog is like you just choose
So I'm
one.
not teaching every
So
student.
that's folks are old.
Damn, I gotta teach it.
Yeah, the class before us had to do orbital or space systems.
Okay. Well, we're reviewing it right now, so it's good. Actually, that's good because last year they were burning it out for me, so they already knew this stuff. I was like, okay, So anyway, you're seeing it now. Let's do an example. Single stage. So we're assuming single stage, but if you have multi-stage, we're gonna sum it. And I'm gonna give you the equations for it, but it's the same principle. So let's say we have an equivalent velocity of 3,048 meters per second, so really high velocity. I have my initial mass of 15,000 kilograms kilograms, and I have my structural mass is 2,000 kilograms, and my payload mass is equal to 1,000 kilograms. Find the burned out velocity or terminal velocity. So find UV, neglecting gravity. So if I'm trying to find UV, UV is terminal velocity, so U is equal to UV from the equation that we were in before is equal to the equivalent velocity multiplied by the natural log of the mass ratio. Question?
For epsilon, what's that word after structural?
Structural, yes.
No, what's the word after structural?
Coefficient. Sorry.
Okay.
Okay. Delta velocity is equal to, or the terminal velocity is equal to my burned out velocity, which is the equivalent velocity multiplied by the natural log of my mass ratio. So all I need is R. So how do I figure out R? Bless you. You can compute R directly by using the that we wrote here, M over MV. But let's do the payload ratio and structural coefficient first. So R is equal to 1 plus lambda divided by epsilon or eta plus lambda is equal to the payload mass plus the propellant mass plus the structural mass divided by, which is the initial mass, payload mass plus structural mass. So we can substitute those in there, take this, multiply by UE, and you got your terminal velocity. It's very, very easy and straightforward. But just because we're not going to have a lot of problems here, so I'm going to do it the longer way. So you can do it, substitute them in there and get it, but I can just do it through epsilon and lambda. I will say epsilon is equal to ms over mp plus the structural mass. So from that, it's equal to my so from that I get my structural mass plus MP. I will get 0.143, and my lambda is equal to ml over ms plus my propellant mass, and that's equal to, sorry, yes. Is equal to 0.0714. So from there, my mass ratio is equal to 1 plus lambda over epsilon plus lambda is equal to 4.997. And from that, I can just get my UB is equal to U equivalent multiplied by the natural log of R, and I will get 4,904 meters per second. I would expect a problem like this in the final, by the way. Right? It's going to be in there. It's too easy not to put it in. Okay. So it's pretty straightforward. All I have to do is bookkeep my mass. You'll realize that, yeah, this is very simple enough that you could do it. If you're trying to find out the propellant mass, you already have the overall mass, you have the payload mass and the structural mass, right? So if you subtract that, you'll get your propellant mass. So MP is equal to MO minus MS over ML. So let's do it for or list the equations for the multiple stages. I'll keep this up. So if I have multiple stages,
Missed it, dude.
so if I have
Front wheel
1,
like
2, 3,
She was there for a minute.
first stage, second stage, third stage, and the final mass or payload mass, right? So if I'm trying to get a longer range, I can have multiple stages. So all I do is have an I factor of whatever stage I have to deal with. MSI for each I stage. So lambda I payload for ith stage. So lambda I is equal to, I'm just reiterating the same equations, Li over MOI plus MLI is equal to the overall initial mass of the stage above it. So I plus 1 over MOI minus MOI plus 1. And the same thing for epsilon MSI over my payload I plus my structural I is equal to my stage structural mass plus my overall minus my overall plus whatever is on top of it. And the same thing with the ratio is the same, 1 plus lambda I relative to the I stage plus epsilon to I stage, and the same thing goes for each terminal velocity for each stage is over epsilon plus lambda I. And for n stage, U of n is equal to the sum of I equals 1 to n of each individual stage. So for multiple stages, it's really the same principle. The difference is your payload or your overall mass is whatever's on top of it. So for each stage, payload mass is, if it's the first stage, well, the payload mass is the second stage plus the third stage plus the payload itself. It's very intuitive in terms of the equations and the same equations. And if you're trying to find out terminal velocity for the total, you figure out for each individual stage and just sum it. But it's the same exact equation. So we'll stop here. In next class, we'll do ionic propulsion.